Hello students, today we are going to study the digital logic families. So let us first understand what is a digital logic family. Now let's take an example. Suppose we have an AND gate and we have an IC for the AND gate. So in IC we know that there are several pins for input, output, VCC, ground, which we can use to operate this AND gate. But internally there is a circuit which makes this particular IC to work as AND gate. So what is that circuit comprised of? That circuit consists of electronic components such as diodes, transistors, resistances, then MOSFETs and so on. So depending on the types of components used, we have different logic families which we are going to discuss. So these are referred to as the digital logic families. So the first type we can see here, it is diode logic or DL. So we can see the circuit. So the major thing is that this circuit consists of these diodes. These three diodes have been shown. So this particular circuit is working as AND gate. That is, VA and VB act as inputs and Vout is the output. The circuit arrangement is such that this particular circuit is working as AND gate. That is, when both the inputs are 1 then the output is 1. So it makes use of diodes and hence it is referred to as diode logic. So this is the first type. Second type is the resistor transistor logic, that is RTL. So this is the symbol of a NAND gate. A NAND gate has been shown here. So we have two transistors in this particular circuit and three resistors. So this is a combination of resistors and transistors. So it is RTL logic. The inputs are VA and VB and the output is Vout. So this kind of a logic family is referred to as RTL. The third type of logic family is the diode transistor logic or DTL. So again we are designing NAND gate using this. So as we can see, the diodes are present here. 1, 2, 3 and 4 diodes are there. And this is the transistor we are using. So the first section of the circuit, this part is acting as AND gate and then we are attaching an inverter here. So after AND gate an inverter is there, so this behaves as NAND gate. So A and B are inputs in this case. There are two inputs and the output is C. So this circuit basically consists of diodes and transistor combination and it is referred to as the TTL logic family. Next comes the voltage levels in the digital logic families. There are four important voltage levels which are taken into consideration. So in order to understand these voltage levels, we must know one thing, like in digital ICs, when we are using them practically, we are checking zeros and ones. So the output or input are set in terms of 0 and 1. But actually these zeros and ones are some voltage levels which are predefined. Like for example, we can take like 0 to 2 volt is acting as a digital 0 and let's say 4 to 5 volt is acting as a digital 1 for example. So for a particular logic family, these levels are predefined. And from where do you find these predefined levels? You can find them through the data sheet which you get when you buy an IC. So in the data sheet, these four important voltage levels are always mentioned. These are VOH, VOL, VIH and VIL. So let us understand what these are actually. So VOH is the minimum voltage level at the output in the logical 1 state under defined load conditions. So at the output, when we are getting a 1, this is the minimum voltage level. So this, suppose VOH is let's say 4.2 volts. So 4.2 volts is the minimum voltage level at the output in logic 1 state for given load conditions. Then we have VOL. What is VOL? It is the maximum voltage level at the output in the logic 0 state. See, when the output is 0, the maximum voltage level which can be there at the output. Then we have VIH. This is the minimum voltage required at the input, which can be recognized as a 1 state. And VIL is the maximum voltage required at the input, that is recognized as a 0 state. So by name you can understand O is referring to output side, I is referring to input side, L is referring to like the logical state when you are taking it as 0, and H is referring to the logical state when you are taking it as 1. So these are the voltage levels mentioned in the data sheet. Another factor which is mentioned in data sheet is regarding the requirement of the current values. So you know, for driving a circuit, there are some minimum current requirements. So again, as voltage, there are 4 current values available. So these are IOH, IOL, IIH and IIL. And these are defined like IOH is the current flowing in an output in the logical 1 state under the specified load conditions. Suppose the output value is 1, then there will be some current flowing through that pin. So that current would be referred to as the IOH. Similarly, we can define IOL, IIH and IIL. Another important feature of a logic family is the fan out value. It is very important. So what is fan out? Fan out is the maximum number of logic inputs of the same logic family that the output can drive reliably. Let us understand what does this mean. Suppose we have a NOT gate. This is the NOT gate. Now, I want to connect multiple NOT gates after this at its output, and it has to drive all of them successfully. That means the circuit should be able to work successfully if these multiple connections are done. So one may want to connect 100 NOT gates, one may want to connect 10 NOT gates. So there is some maximum limit, like how many maximum number of possible NOT gates can be connected at this output simultaneously. And what does that limit depend on? That limit depends on the current driving capability. Like every NOT gate connected at the output must be having a current sufficient to drive the circuit further. So this particular value is referred to as the fan out. Like suppose for this particular circuit, I can have 5 maximum NOT gates connected at the output for like proper working. Then if I connect 6 NOT gates, there would be a problem in the circuit. So 5 would be the fan out for this circuit. And how do we find out mathematically? The DC fan out can be found by this particular formula. It's very important, asked in gate exam many times. Like these 4 values are given to us: IOH, IIH, IOL, IIL, and we are told to find the value of fan out. So we can find these two ratios, and out of these two ratios, whatever is the minimum value, that will give us the fan out value. The next parameter, which is very important feature for a logical family, is the propagation delay. Let us try to understand what is the propagation delay. So in general language, if I say if there is a gate, like we take NAND gate for example, so like the time the input takes to propagate to the output side is referred to as propagation delay. This occurs because there are certain components used in between which have some inherent delay in them. So let us take the example of this waveform. So here Vi is denoting the input and V0 is denoting the output. So this is working as a NOT gate. So 1 will become 0 and 0 will become 1. So this is our input. So we can see initially the input is 0 and it slowly rises to a value of 1, and then again it falls back to a value of 0. And V0, we can see it will be inverted from Vi because it is acting as a NOT gate here. So initially it is 1. It takes some time to fall to 0, and then again it takes some time to rise again to 1. So what we do, we take the 50% value for both the waveforms. Like suppose this particular amplitude is, let's say, 1 unit, then we take a line at 0.5. So this is a 50% line. So where the 50% line intersects this curve, we take this point. We mark this point. Again, another point, we get this one. Similarly, we take the 50% points for the V output waveform. These are taken. Now, we take the difference between, like suppose this is point 1 and this is the output point 2. We take the difference of time for these two, and this particular value is referred to as TPD-HL. Again, another point, we get this one for input and this one for output. Again, we take the time difference for these. This is referred to as TPD-LH. Now, we obtain two propagation delay times and take the average of these. When we take the average, we get the final value of the propagation delay TPD. How we take the average? We just add them and divide by 2. Now, this is the propagation delay. And if we multiply this with the average power for the circuit, we get the speed power product or SPP. This topic is also very frequently asked in the GATE exam. Noise margin is another important property for a given logic family. So what does the noise margin mean? Let's try to understand. Suppose we know, suppose I have a sine wave. Now, when a sine wave propagates through a medium, then there may be some distortions or some noise added into this. So what will happen? This sine wave will not remain as it is, and there will be some additions or subtractions in the amplitude. So noise margin is something the amount of noise which can be added to the signal without affecting the output. Okay, so this is the noise margin, and how we find it out mathematically. To find the value of noise margin, this is the formula. So we have to find out VNH, we have to find out VNL, and take the minimum value out of these two. And how we find VNH and VNL? VNH is given by VOH minus VIH, and VNL is given by VIL minus VOL. So these values are obtained from the data sheet, and we can find VNH and VNL and take the minimum out of them. So this will give us a noise margin, that is the margin, the amount of noise which can be added to a signal without affecting the output. Noise margin is a topic which is generally asked in ESE exam. Now let's see what is the purpose, why we are studying these different digital logic families. What is the purpose? We have seen various properties like propagation delay time, fan out. Then you have seen how the structure of these particular families varies. So we have different options, and we can select the type of digital logic family we want to employ for our project or anything else as per the requirement. Like there will be some projects which require low power dissipation. There will be some projects which would require fast circuits. So we have to choose the family as per that. So, suppose I have NAND gate. NAND gate can be designed using many logic families, but I will take the one which suits my requirements. So we must be aware what all families are available. So next type of family is the TTL. TTL is basically bipolar transistor logic. So as you can see the diagram here, we have several transistors in this. So this is an example of a TTL two input NAND gate. Now, there are certain features in this circuit you have to observe. There are multiple emitter transistors also present. We can use multiple emitter transistors like this. So there are two emitters in this. Then we have a totem pole transistor arrangement that can be viewed from here. So here there is a transistor, here there is a transistor and a diode in between. diode in between these two transistors. So this will help in forming the totem pole transistor arrangement. Another TTL variation is the Schottky series. So like we will observe like in BJT, the circuit may get slow because the transistor goes into saturation and again it has to revert back from saturation. This takes a lot of time. So in that case, what we can do, we can use a Schottky diode because it has a lower value of forward bias. So what will happen? It will prevent the transistor from going into saturation. So that's why this particular Schottky series TTL series would be faster. Another digital logic family is the emitter coupled logic, that is ECL. So it is very fast. It is the fastest logic family which is available, but it has low noise margin and a large power dissipation. So sometimes there are applications where power dissipation is not a consideration, but we want very fast circuits. So what we do, we use the ECL series. The logic levels we use are given here, and we can design ECL inverter here. CMOS or complementary metal oxide semiconductor family is another family, and it has a very low power consumption. So where we want low power, we can use CMOS, and it provides full swing. Full swing means the in like lower to higher output range. It gives a full span, like from 0 to 10 volt, for example. And we can design NOT gate, NAND gate, and all using CMOS devices. Thank you so much for watching the video.